So this little video is going to deal with two concepts, karyotypes and pedigrees. Karyotypes will not take very long. It's just a tool that scientists use to diagnose some prenatal issues most often. This is a picture of one organism's entire somatic nucleus. So that means that it's a diploid cell, and what they do is they take a kind of a sample of a nucleus, and they'll break the nucleus open so all the chromosomes are present. And this is obviously not real chromosomes, but this is the most oftentimes you'll see it in an actual diagram. What you notice is they first are recognized as a replicated state. So the easiest time to actually do this process is during a metaphase process when it's actively dividing. They wouldn't do this when the cell is during interphase because the chromatin is not very easy to organize. So this is why you often see them in replicated state. So it's kind of like they have tetrads, and they've ripped all the tetrads and put them in a size order. And this is a human example. So you can see the numbers range from 1 to 23. So that's the reason why it's human. You can recognize that in order to count, this is the haploid number. So there are 2 chromosomes that are homologous to each other at each number. So that brings you up to 46. So the way that they do this, if you look at the first chromosome comparing it all the way through to the first 22, these are the autosomes. And autosomes are non-sex determining chromosomes. A male or female will look identical in terms of their autosome numbers. So what they do is they find the match, or the homologous match would be the same size and same shape. For this instance, what they do to represent homologous chromosomes, they have the same banding pattern. So they kind of look identical to one another. Theoretically, homologous chromosomes are not identical, but for the ability to differentiate the different chromosomes in this little activity, they often make them identical, but it's not really true. But what we have here, you have the homologous chromosomes, and they're in replicated state. They line them up in size order. I don't know why they necessarily skip. There's no rhyme or reason as to potentially why is there a gap here, but just when you create a karyotype, you pull out all the autosomes and you line them up by size order. And then this last pair right down here, you'll notice that they are 2 different sizes because that would represent the X chromosome and the Y chromosome. So the Y chromosome is smaller, the X chromosome is larger. So I would recognize this as a male karyotype. A female, you'd have to really have a trained eye to recognize that that was the X chromosome. Many times the worksheet that you work with will actually identify the X's and Y's immediately so that you kind of can pull them out. Since you're pretty new to this, you wouldn't have the trained eye, but to a person working on this under the microscope, they would have to kind of know what size they're looking for and maybe a banding pattern for them to know that that's the sex chromosome, especially for a female. The male might be a little bit easier to recognize. But within this karyotype, you get a lot of information. You can obviously get the sex of the organism if that was something you were curious about before a child was born. But also they look up how many chromosomes are at each autosome number. So this one shows a typical karyotype where there are 2 homologous matches for each of the numbers. But then there are some times where you have a mishap in meiosis and maybe you inherit an extra chromosome. Very often chromosome 21 is inherited as a 3rd time. So that would make it a kind of diagnosed issue that we might know as Down syndrome, but a karyotype is just a picture of one cell's nuclear arrangement in size order. And we use the word autosome and we use sex chromosome to then go into a pedigree, which a pedigree is tracing. It's a family tree. You have to kind of know what the symbols represent, so I'm going to do that very, very quickly. On a pedigree, it is standard that you have squares and circles. A square represents a male, a circle represents a female. A direct line between male and female would mean some type of marriage or mating scenario has happened. Roman numerals over here represent the generation. The first generation would be the oldest generation in the family, working your way down. You often identify, because names are not applied to this, you often identify by generation, and then you start counting from left to right. So this would be generation 1, person 1, generation 1, person 2, so on and so forth. When you get to generation 2, you restart the numbering. So this would be generation 2, person 1, generation 2, person 2, and so on, and then it would keep going for as many generations as you see fit on your pedigree. Now, the role of a pedigree is to identify a specific trait, and the way that they identify that specific trait is by shading in the person within that actual pedigree. So all that shading means is that they are affected by the trait that you are interested in tracing. That doesn't mean that it necessarily has to be recessive. It doesn't mean that it has to be dominant. That's actually going to be the role of you in this process, is you're going to see a pedigree, and then you have to kind of use the clues of the actual family members to decide, is it, first off, autosomal? Is it recessive? Or is it sex-linked, dominant? So there's all these varieties that you can do. So affected does not mean one or the other in terms of recessive or dominant. Affected only means that they have the trait. So every one of these 4 individuals, I'm saying, has affected by the same trait. That could be a disorder, or it could be as something as simple as attached earlobes. So we're not talking something that has to be necessarily a disease or disorder. It's just a trait that has some genetic component to it. So this is already under the category of autosomal recessive, so I'm going to show you why it has to be recessive and what we do with it from there. So the clue for an autosomal recessive pedigree is looking for 2 parents of an affected individual that are not affected themselves. This can only happen in a scenario where they are carrying a recessive allele behind their dominant phenotype. So if you reverse it, there is no way that if the affected individual here was a dominant trait, they could have 2 parents of recessive phenotype. There is no Punnett square that Mendel would produce that would kick out a square that would be the opposite if they were recessive. So that means that this female, male, and male must have a recessive phenotype, because their parents are showing the opposing phenotype, which would then have to be dominant. So it forces all the unaffected people to be dominant. So what I'll do is I go in and I'll assign a letter A. It's the simplest thing to do. I'll go into those individuals and I'm going to determine genotypes as much as possible. Since I've established that this has to be a recessive trait, we'll talk about why it's autosomal when we actually start discussing sex-linked information. So for right now, I'm going to let you know that it is an autosomal trait. So from here, I can go in, and for all the other people that are unaffected, I can go in and assign a dominant allele to them. The rest of this is now based on the shading pattern as to what is the second allele. Do I know it for every other individual on here? So if I go through, I recognize that this female could only have inherited 2 recessive alleles if each parent passed down 1 to her. So that means both of these parents must be heterozygous in nature. There's no guarantee that 2 heterozygous parents, when they have a dominant offspring, if you do that pedigree or Punnett square in your head, some of the squares will have homozygous, some of them will be heterozygous. So I can't really decide this because there's not enough information to decide that. So when I don't know enough, what I do is I put a slash and dash. That tells me it could be either, there's either possibility at this moment. When I go here, I kind of go look at this. These people kind of help me fill in the previous and post generation. So this male had 2 offspring. Every time he has an offspring, the only option he can pass down is a recessive. If it's not seen immediately, you can then deduce that they must also have the recessive, because he only has that option. If you look at him, he has to be an offspring of these 2 individuals. They also must be dominant phenotype. So it's another indication this is a recessive. And because he has both recessives, that means both parents must carry it. So that's another scenario. A basic clue that some textbooks will tell you about how to identify if something is a recessive trait is that it skips generations. Technically, to an individual right in the beginning, if they're not really looking at this carefully, they might see like, oh, it's in every generation, but it doesn't. These people are not blood related. So it kind of is more technical to say that recessives have the ability to skip blood relationships through generations. So the last one that I have here is this. And since we don't know anything about her parents, and her offspring don't give any clue that she's carrying a recessive allele, then she also is another slash and dash. So that would be an acceptable autosomal recessive pedigree. That's what we're going to be doing throughout this chapter. All right. Then, if we flip, you can press pause if you have to draw these out. But what we have is an autosomal dominant pedigree. So I did something very similar with a different pattern. I have my generations 1, 2, and 3. And I have to prove why the affected people on this would be autosomal dominant. So I often, in my mindset, I try and say why it can't be the other. And when it can't be the other, then it kind of narrows down what your options are. But autosomal dominant, this kind of is your clue. I'm looking for two parents of the same affectedness, and I look to their offspring. Is it possible, if they had a recessive trait, could they have an oppositely affected individual, which would be the opposite phenotype or dominant in that case? Is that possible? It is not. But can two dominant parents have a recessive offspring? That is possible. So what you do, this is the clue that this is a dominant phenotype. So I'll go in, and with dominant, I can only assign one letter to begin with. All these other people must be recessive because of this scenario. As soon as it's dominant for one family, it's the same trait being traced throughout. So I kind of have to assume that everybody that is unaffected or not shaded is the recessive phenotype. So I plug them in immediately. Don't look at numbers. I did this strategically where I have 1, 2, 3, 4, 5, 6 unaffected and 1, 2, 3, 4, 5 affected. Some students immediately think that numbers have something to do with it. Don't get kind of put into that scenario. Numbers do not have anything to do with if it's dominant or recessive. You've got to look for the clues of the family. So from here, to plug in the second alleles, it's actually, if I look up here with this male, they have an offspring that is recessive. One of these recessives must have come from this parent. That means the other one had to arrive from the father. This daughter received the dominant allele from dad. The only option from mom is for her to receive the recessive. Over here, because of this son, there is only the ability for these two parents to be heterozygous. Any other Punnett square where there would be a homozygous person up here would then render this impossible. All right? And then here, the same situation, two heterozygous, they have the ability to both pass down their dominance, or one or the other can pass the dominant while the other passes the recessive. So there's not enough information, so I will do a slash and dash. So these are all autosomal. I really didn't look to see if they were male or female. I was just looking at patterns, and that's how you think about autosomal traits. When we did Mendelian Punnett squares, and they were all autosomal, you didn't care if it was male or female. That's the same case here. So I'm going to create a second video that deals with sex-linked because there is a different mindset that you have to approach. But those would be the autosomal dominant and recessive pedigrees. There are some practices that you can do. So for example, let me find a good one. So for example, if you look at this, can you tell just based on the shading pattern what inheritance pattern this would be? Would this be an autosomal dominant or recessive? Can't just look at numbers. I would have to prove it. So you would have to say that this is an autosomal recessive, and what your clue is right here, or right here. The idea that she cannot have a dominant trait if her parents are both recessive. So the only option is, and sometimes I ask you to tell you what it cannot be. So this cannot be dominant, specifically autosomal for right now. This cannot be autosomal dominant because this proves it. So I would go in and I'd say, all right, well then she and he must be heterozygous. She must be homozygous recessive. So we'll do more practice with this, but I wanted to kind of start this video with just those two examples.